Spanning across 105,700 light-years, the Milky Way galaxy is estimated to house upwards of 100,000 to 400,000 exoplanets. The term exoplanet meaning any planet outside our solar system. Of those exoplanets, NASA has confirmed discovery of 5,572, with another 10,065 categorized as unconfirmed discoveries still being analyzed. And out of the confirmed exoplanets, the Habitable Worlds Catalog lists only 63 as habitable. With so many undiscovered exoplanets out there, we haven't even scratched the surface. Yet could these 63 exoplanets potentially be Earth 2.0, a planet similar enough to Earth to enable the existence of life as we know it? You might have encountered the catchy term Earth 2.0 in headlines or articles, suggesting the discovery of a new planet deemed ideal for human habitation and colonization. Yet despite the hype, they are not as hospitable as you think. Many of these so-called Earth-like planets face extreme conditions that challenge the possibility of human colonization. Whether it's elliptical orbits causing scorching temperatures and icy wastelands, or intense gravities that would crush our bodies over time, these planets present formidable barriers to habitability. To understand this better, let's dive into a few key points to consider. First, for a planet to be deemed suitable for human life, it must share Earth's solid composition. Unlike gas giants, where existence would necessitate living within protective enclosures, our search is for a world where we can roam freely, akin to our home planet. Gas giants, despite their awe-inspiring size and presence in our solar system, hold little promise for harboring life as we know it, as they typically lack solid surfaces for landing or living. Their incredibly thick atmospheres with high pressures and temperatures, along with violent storms and winds, cannot support the kind of ecosystems humans need for essentials like food, water, and breathable air. Instead, let's focus on finding rocky terrestrial planets with solid surfaces located within their star's habitable zone, where liquid water can exist on the surface. These terrestrial havens offer the best chance of finding conditions compatible with life as we understand it, potentially holding the key to finding the next Earth. In our search for Earth 2.0, one of the first things we look at is how the planet orbits its star. It turns out a stable, nearly circular orbit is key for humans to stand a chance. Take Earth, for example. Its almost circular path around the Sun keeps our climate steady and livable. On a circular orbit, a planet doesn't swing too close or too far from its star, avoiding wild temperature changes. This steady distance keeps the climate stable, which is just right for lakes, rivers, and oceans of liquid water essential for life as we know it. But what about planets on elongated or elliptical orbits? They face a tough time. These planets move closer to their star, then drift away, causing dramatic shifts from hot to cold. Such extreme changes make it hard for life to get started or keep going. That's why analyzing temperatures within a habitable zone is crucial for assessing a planet's potential to support life. Also known as the Goldilocks zone, this is a region around a star where conditions are just right for liquid water. Planets too close to a star, like Mercury, get too hot for life. Those farther away, like Neptune, become too cold. This range depends on the star, but typically falls between 0.7 to 1.2 times Earth's distance from the Sun for stars similar to ours. Moving from the ideal temperatures of a habitable zone, our focus shifts to the atmosphere, the crucial layer that determines a planet's habitability. The ideal planet must have an atmosphere rich in oxygen, nitrogen, and water vapor, devoid of toxic elements, and adept at regulating temperature while shielding against radiation. Oxygen, the air we breathe, forms a vital component, allowing complex organisms to thrive. Nitrogen provides stability, and moderate temperature extremes. Water vapor, often seen as clouds, plays a crucial role in the hydrological cycle, transporting and distributing water across the planet. Therefore, when searching for potential homes beyond Earth, a suitable atmosphere becomes paramount. Let's take GJ 1132b as an example. Though a rocky planet, it was observed by the Hubble telescope to have what the scientists, according to their theory, call a secondary atmosphere. Based on a combination of direct observational evidence and inference through computer modeling, the team reports that the atmosphere consists of molecular hydrogen, hydrogen cyanide, and methane, and also contains an aerosol haze. Modeling suggests the aerosol haze is based on photochemically produced hydrocarbons similar to smog on Earth. With this kind of atmosphere, it'll be very dangerous for humans to live on. Another important item to consider is the type of star supporting the potentially habitable exoplanet. Our Sun, a 4.6 billion-year-old G-type yellow dwarf, burns relatively fast and has a lifespan of about 10 billion years before turning into a red giant. Despite the yellow dwarf's shorter lifespan compared to red dwarfs, these stars have been ideal for life on Earth. However, they are uncommon in the Milky Way, accounting for only 7% of the total number of stars in our galaxy. On the other hand, red dwarfs are much more prevalent, comprising 75% of the stars in our galaxy. These stars have lifespans that range from 100 billion years to 10 trillion years, depending on their mass, some potentially surpassing the lifetime of the universe. Yet planets orbiting red dwarfs face various drawbacks due to the nature of their host stars. Let's talk about more of these drawbacks. Habitable planets orbiting red dwarfs present a unique set of challenges. Firstly, the Goldilocks zones of red dwarfs are much closer than those of yellow dwarfs, resulting in exoplanets orbiting much closer to their stars. This proximity, however, reveals the second characteristic of red dwarfs, which is their instability. With flares that are 100 to 1,000 times more powerful than those of our Sun, red dwarfs pose a significant threat to their planets, bombarding them with frequent bursts of plasma and radiation. These outbursts can strip away atmospheres and boil liquid water on planets within the star's habitable zone. Imagine if the Earth were without its atmosphere. The scorching sun would beat down relentlessly, raising surface temperatures to unbearable levels. Lethal ultraviolet radiation would bathe the planet, sterilizing any potential for life. Even water, the elixir of life, would struggle to exist in liquid form, evaporating rapidly into the harsh vacuum. To combat this, a planet must have a strong magnetic field to deflect harmful rays and solar winds. The magnetic field acts as an invisible force field, shielding the planet against harmful radiation and charged particles from the solar wind. Earth provides a notable example of this protective mechanism. Our planet's magnetic field, generated by the movement of molten iron in its core, deflects most of the solar wind and radiation, fostering a habitable environment where life has thrived for billions of years. The magic happens in the outer core, a layer of superhot liquid iron, about 2,200 kilometers below our feet. This molten metal acts like a giant conductor, swirling and churning due to the Earth's rotation and heat escaping from the inner core. As this superhot liquid iron moves, it interacts with Earth's rotation, creating electrical currents. These currents, in turn, generate their own magnetic field. The magnetic field generated in the core extends outward, enveloping the entire planet and stretching far into space. This mechanism, responsible for the generation of the Earth's magnetic field, caused by convection and conduction currents in the fluid core, is known as a geodynamo. Ironically, while solar winds can be dangerous, they also create stunning auroras, also referred to on Earth as northern lights or southern lights. In the ionosphere, the ions of the solar wind collide with atoms of oxygen and nitrogen from Earth's atmosphere. The energy released during these collisions causes a colorful, glowing halo around the poles. These beautiful displays of light show how the solar wind interacts with Earth's magnetic field, revealing the incredible beauty of our planet's relationship with the Sun. Now, without rotation imparting momentum to the liquid metal in its core, the resulting magnetic field would inevitably be weaker. For example, Proxima Centauri b, an exoplanet 4.2 light-years away, discovered in 2016 and 1.27 times the mass of Earth, is the closest potentially habitable exoplanet we've discovered yet. But due to the weak magnetic field, it's not a suitable planet to live on, as it closely orbits a particularly chaotic red dwarf that consistently emits solar flares. Then there's also another problem that Proxima Centauri b has. It's tidally locked, meaning that one side of the planet permanently faces its star, because the planet takes just as long to rotate around its own axis as it does to revolve around its star. The contrast between the day and night sides of a tidally locked planet can lead to extreme temperature differentials. On the day side, temperatures may soar to blistering levels, causing materials to melt and water to evaporate rapidly, rendering the environment uninhabitable without advanced cooling systems. Conversely, the night side experiences frigid temperatures, potentially plunging below freezing, making it difficult for any life form to survive without adequate insulation and heating. The stark temperature differences between the day and night sides can create turbulent atmospheric conditions. Hot air rising from the day side and cold air sinking from the night side can generate powerful winds and storms, leading to unpredictable weather patterns. This atmospheric instability could pose significant challenges for any attempts at colonization or sustained habitation. The narrow band of habitable conditions known as the Terminator line, where the day and night sides meet, may be the only region where life could potentially thrive. However, this zone would be subjected to constant flux as the planet orbits its star, causing significant shifts in temperature and environmental conditions. This instability could make it difficult to establish stable ecosystems or infrastructure for long-term human settlement. Another problem with red dwarfs is that they are also the dimmest stars, with luminosities between about 0.01 and 10% that of our Sun, emitting most of their light in the red and infrared wavelengths. And though exoplanets within a red dwarf's habitable zone are typically closer, those exoplanets would still have particularly chilly, gloomy atmospheres, which again would be unsuitable for plant life. And speaking of life, another thing we need to consider when looking for a potentially habitable planet is the microbiological life that may already be present on that exoplanet. Because presumably, if a planet would be habitable for us, chances are the building blocks for life are already forming there. Which brings us to the potential threat of microorganisms. Invisible to the naked eye, yet wielding immense power, they might pose both threats and benefits if humans were to colonize a habitable planet. Research suggests that microbial life is remarkably resilient and adaptable, capable of surviving in extreme conditions such as high radiation, extreme temperatures, and low nutrient availability, characteristics that could aid in colonization efforts. For instance, extremophiles like Deinococcus radiodurans have demonstrated resistance to radiation levels far exceeding those found on Earth, hinting at the potential resilience of microbial life on other planets. However, this resilience could also present challenges, as pathogenic bacteria and viruses could similarly survive and thrive in new environments, posing risks to colonists' health. Studies have shown that microbial ecosystems play crucial roles in regulating planetary processes, such as carbon cycling and nitrogen fixation, suggesting that understanding and managing these microscopic inhabitants would be essential for maintaining the stability of a colonized world. In the event of encountering dangerous microorganisms on a habitable planet, we might rely on spacesuits or enclosed habitats. Advanced spacesuit technology equipped with sophisticated filtration systems might protect us from harmful pathogens while allowing explorers to venture outside controlled environments. However, prolonged reliance on spacesuits and enclosed habitats might restrict exploration. Further research is needed to understand the microbial life on alien planets, given the lack of direct on-planet observations. In searching for another habitable exoplanet, the final key point we will consider is gravity. Kepler 452b, the first Earth 2.0, resides within the habitable zone, has a similar distance from its yellow dwarf star, and shows potential for liquid water. However, it is a super-Earth with a probable mass 5 times that of Earth and surface gravity twice that of Earth's, raising questions about the impact of gravity on habitability. As humans, we have a limited tolerance for high gravity conditions with a survivability limit of approximately 4 times that of Earth's. Even double the gravity of Earth can cause significant discomfort, with the weight sensation making breathing difficult and increasing the risk of bone fractures from minor falls. This challenge affects every individual, regardless of their age or physical condition, making every step laborious. Living under double gravity is likely to exhaust most individuals, as their hearts work incessantly to circulate blood, creating a perpetual feeling of exertion even while at rest. Triple gravity would add another person's weight, further exacerbating the issue. On the other hand, reduced gravity might initially seem liberating, but it comes with significant health risks. Astronauts, for instance, suffer from bone loss, muscle atrophy, weakened hearts, and compromised immune systems while spending months on the International Space Station. Even with daily exercise, long-term prospects in low-gravity environments remain grim, posing a significant challenge for NASA as it plans human outposts on celestial bodies like the Moon or Mars for just a few years. As a species, we have made significant strides in evolution, advancing from primitive cave-dwelling to technologically advanced beings. However, when it comes to space exploration, we appear to be out of our element. Despite scrutinizing billions of planets within the Milky Way, discovering a suitable destination akin to Earth remains an elusive goal, akin to finding a needle in a haystack. The quest for Earth 2.0 is complicated by numerous variables such as gravity, temperature, radiation, air quality, and water availability, which must be considered. Additionally, the search is further challenged by the many planets that evade detection, making the task even more daunting. Launched in 2009, the Kepler Space Telescope observed 13 million stars until its deactivation in 2018, discovering over 2,600 planets. However, it fell short of finding an Earth 2.0. This was partly because Sun-like stars turned out to be noisier than expected, so it required longer observation times. Then, in 2013, 2 of the observatory's 4 reaction wheels broke down, making long-term observations impossible. A new hope arises with the Chinese mission, Earth 2.0, set for launch in 2026. Led by a team of 300 scientists and engineers, this mission aims to scan for Earth-like planets orbiting Sun-like stars. Equipped with specialized instruments, including 6 30-centimeter telescopes and a 7th telescope designed to look for micro-lensing events in which the gravitational field of a star focuses the light from a distant star behind it. The telescoped spacecraft, Earth 2.0, will search for changes in star brightness and micro-lensing events as signs of nearby planets. It will be positioned at the L2 Lagrange point opposite Earth from the Sun, where gravity is balanced for stable orbiting, offering an unobstructed view of space while minimizing fuel needs for the telescope. Earth 2.0 will orbit for 4 years, transmitting 169 gigabytes of data daily. Simulations suggest it could detect around 29,000 new planets, including nearly 4,900 Earth-sized ones, potentially uncovering 10 to 20 Earth 2.0 candidates by 2030. The notion of discovering Earth 2.0 demands cautious consideration. Before any assertion of a planet's suitability for human habitation, it's crucial to conduct first-hand exploration of the vastness of space. The challenges involved in finding a suitable abode for humanity are immense, from gravitational strains to the perils of alien atmospheres. Despite the difficulties, our unyielding curiosity and indomitable human spirit drive us in search of a cosmic twin. While the possibilities tantalize, certainty remains elusive amidst the vastness of the universe. The pursuit of this quest endures, beckoning us into unknown realms. As we continue to explore the cosmic frontiers, we are reminded of the remarkable challenges that lie ahead. We invite you to leave a like on this video and subscribe to the channel for more captivating content. Thank you for joining us on this journey, and until next time, keep looking up.